Physics can feel a little intimidating sometimes, right? But what if I told you there's this one simple idea, a concept so logical and powerful, it's kind of like a secret key for solving problems? Well, that's exactly what we're diving into today. Let's talk about the principle of homogeneity of dimensions. Okay, so here's what we're going to cover. First, we'll get into the golden rule of equations. Then, we'll see how to actually check dimensions step by step. We'll even solve for some unknowns, talk about a few tricky situations like powers and signs, and wrap it all up with how this is going to be your superpower for the NEET exam. All right, let's kick things off with a super simple, common sense idea. Seriously, this is the foundation for everything else we'll talk about. And honestly, it's something you already know deep down. So take a look at this. 4 seconds plus 3 kilograms. It just looks wrong, doesn't it? It feels weird because, well, it is. You can't just add time to mass and get a sensible answer. They're totally different things. And that right there, that's the golden rule. That's it. Physics works the exact same way. You can add a force to another force, sure. You can add a length to another length, but you just can't mix and match them. It's that simple. So this common sense idea actually has a fancy name. The principle of homogeneity of dimensions. But don't let the name scare you. All it's saying is that for any real, valid physics equation, every single piece of it, every term on the left side and every term on the right side, has to have the exact same dimensions. If they don't match, the equation is busted. Simple as that. Okay, so now that we've got the rule down, let's put it to work. We're going to use this principle as a tool, like a little detective kit, to check if any physics equation is dimensionally correct. Think of this as our little cheat sheet, or our toolkit for this job. These are the dimensional formulas for some of the most common things you'll see, like velocity, force, and energy. It's a really good idea to get comfortable with these, because we're going to be using them a lot to break down equations. All right, let's grab a familiar equation from kinematics, one you've probably seen a bunch of times. We're going to put on our detective hats and check out each piece of this equation to see if it actually follows our golden rule. Okay, let's do this step by step. First, let's look at the left-hand side. We just have S, which is displacement, so its dimension is just length, or L. Easy enough. Now, for the right side, the first term is UT. Okay, U is velocity, which is LT to the minus 1, and we multiply that by T, which is time, T. The T to the minus 1 and the T cancel each other out, leaving us with just L. Awesome, so far so good. Now for the last piece, half AT squared. First things first, that number half, it's just a constant. It has no dimensions, so we can totally ignore it. Then we have acceleration, A, which is LT to the minus 2, multiplied by time squared, T squared. And look at that. The T to the minus 2 and the T squared cancel out, and we're left with, you guessed it, L. So let's check our work. We have L on the left, the first term on the right is L, and the second term on the right is L. They all match. The equation is dimensionally correct. Perfect. But wait, there's more. This principle isn't just for checking if an equation is right or wrong. We can actually use it like a superpower, like we're solving a logic puzzle, to figure out the dimensions of unknown things in an equation. And this is a super, super useful skill to have. All right, check this out. Let's say we're given this equation, V equals A plus BT. We know V is velocity and T is time, but we have no idea what A and B are. So how in the world can we find their dimensions? Well, we're going to use our new favorite tool, the principle of homogeneity. Here's our thinking. The first clue is the plus sign. Since we're adding A to B, T, our golden rule tells us they absolutely must have the same dimensions. And what do they equal? They equal V, which is velocity. That means all 3 terms have to have the dimensions of velocity. So boom, right away we know the dimension of A must be the same as velocity, which is LT-1. Now for BT. The dimensions of the whole term BT also have to be LT-1. So the dimension of B times the dimension of time, T, equals LT-1. A little bit of simple rearranging tells us that the dimension of B has to be LT-2. And hey, that's the dimension for acceleration. See how that works? Okay. Now let's get into some of the special cases. There are a few more important rules you gotta remember, especially when you run into things like powers or functions like sine, cosine, or even logs. This one is huge. You absolutely have to remember this. The argument of any trig, log, or exponential function has to be dimensionless. I mean, think about it. You can find the sine of an angle, like 30 degrees, right? But can you find the sine of 30 kilograms? No way, that's just nonsense. So the stuff inside the function, what we call the argument, has to be a plain old number with no units. So let's look at a classic wave equation. See that whole chunk inside the sine function, the omega t minus kx? Our rule says that entire thing has to be dimensionless. But wait, there's more. Remember how you can only add or subtract things with the same dimensions? That means if the whole thing is dimensionless, then each part must also be dimensionless. So omega t has no dimensions, and kx also has no dimensions. This is such a cool shortcut for finding the dimensions of things like omega and k. Okay, it's really important to know that while this tool is amazing, it does have its limits. It's not a magic wand. For instance, it can't tell you anything about those dimensionless numbers, like the half we saw earlier, or constants, like 2 pi. And here's the biggest one. Just because an equation is dimensionally correct, it doesn't automatically mean it's the physically correct formula. Think of it like a spell checker. It can tell you if a word is spelled wrong, but it can't tell you if you've written a good sentence. So, let's bring this all home. Why did we learn all this? Because when you're sitting in the NEET exam, where every second counts, this principle isn't just a concept, it's a strategy. It's one of your best tools for knocking out wrong answers and doing it fast. Okay, picture this. You're in the exam, and you see this equation is one of the multiple choice options. Your first instinct might be to start calculating, but wait, just look inside the sine function. You see vt. What are the dimensions of that? Well, velocity is lt-1, and time is t. Multiply them, and you get L, a length. And we just learned the argument cannot have dimensions. So this equation is impossible. It's wrong. You can literally just cross it off your list in under 5 seconds and move on. No complex math needed. And that's the whole point. This is such a game changer. Use dimensional analysis as your very first check. Before you do anything else, just quickly scan the options. You can often spot the wrong answers right away and eliminate them. It's going to save you so much time and really boost your confidence. So I'll leave you with this one last thing to think about, which really ties everything together. If an equation is dimensionally correct, does that 100% guarantee it's the right formula? Remember what we said about the limitations? Keep this amazing principle in your back pocket. Use it as a quick check. Use it to knock out wrong answers. And I promise, you'll start to see that physics is a lot more approachable than you think. I really hope this helped. You can totally do this.